Hi, I haven't actually made a video in about a week, so I hope I remember how to do it. I didn't get any emails from anybody, so I'm not sure if you tried this. I'll leave it open, but you'll probably, well, you'll see if you actually calculate it. You will never win at this pop quiz. But the reason I put this here is actually the normal is a very nice, the normal curve, which is the bell curve, is a nice approximation to many discrete distributions. And you might think that's a little bit illegal because you're taking something that's discrete, defined at nice, like points. Let me draw a little picture here. Maybe at, x equals 1, x equals 2, x equals 3. Maybe you have this, a discrete function, but sometimes it's very nice to go ahead and put a curve over it. In this case, a normal curve, if it so fits, and define probabilities instead of summing. We can look at an integral, and it will be a nice approximation. I mean, think about when you learn integration and you just have Riemann sums and you have these little boxes. If they're tight enough, the area in the little boxes is the same thing as integrating over the curve. So essentially that's what we're doing, and so it's not terrible to fit some kind of curve over a discrete distribution, especially when you have a large range and it becomes almost impossible to sum over the values you have. So I was having you play a ESP game. I think this is a very interesting example. Back in the 30s, people were trying to figure out if ESP really existed, and they did an experiment. And they had down here I'm showing you, they had 32 subjects that had 60,000 guesses. And when they showed them these figures, 12,489 times the people who guessed were correct. And in general, if you had a binomial distribution where there's 5 different cards, there's a fifth of a chance that someone would guess the right card. So out of 60,000 guesses, we would expect, this is a binomial, we would expect 12,000 correct guesses, and we got actually this many, which is way out in the right tail of a normal curve, which seems like just by guessing that's almost impossible. So they were trying to say from their findings there's reasons to believe that ESP exists, and this is one of the first examples that people use the normal to approximate the binomial. You can see right here as a binomial, this is the sum we would be using. You can see all the little boxes. Maples falls apart if you try to go ahead and sum this. You would be summing past 12,489 on a binomial, and it just crashes. So the best way to do it would be to slap a normal curve on this thing and then integrate past this little part, which is very, very negligible area, as you'll see when I actually do it. This is the probability being past that. So in other words, if they were just guessing, almost impossible. So the point was they were trying to say ESP existed, and that is not for us to discuss, but I think it's an interesting study. So 7.2, probably it is the most important continuous curve. So chapter 6, we looked at continuous functions. 6.1 or 7.1 was on the uniform, which was just that really nice curve that's defined from A to B. It's just a nice straight line. Area under the curve is 1. It's just a rectangle. You can think we're doing the normal just the way we would do a uniform, except the density function is a lot nastier. It has a square root of 2 pi in the bottom. So anyway, the guy that found or is named for the normal curve, it's also called the Gaussian curve, is Carl Gauss. And if you have a Zane Deutschmark, you can see on it right there is the normal curve, and they actually have the probability density function written on a piece of money, which is so interesting. So when you come back to school, if you want to see it, I have this bill. I have 2 of them. I bought the last one on eBay for like $10. I mean, it was worth it to me. It's just really cool because on this piece of money you can slightly see there f of x is written, and that f of x is not nice. It's 1 over square root of 2 pi times e to the negative x squared over 2. And that formula is sitting right there on that piece of money. So if you were a German student, you'd just be like, oh, I better take my Gauss money to the test, and there you have the nice probability density function. I think that's really cool. So again, this normal curve, there's so many reasons that it fits so many situations. If you do something enough times, right, you tend to converge to the center, which is the bell part. I mean, anything like, intelligence, height, you always have your extremes, left, right, tail, but most things fall right in that bell. This is, well, I would love to show you this. I have one of these Quinn Clicks. If you press on that, it shows you, balls dropping. It's kind of like plinko, or is that what they call that on Price is Right? They call that plinko? I don't know. My students one quarter said, oh yeah, we have one at our fraternity. It's called Drinko. But that's a whole different, we probably don't want to talk about that. But anyway, that's really, really relaxing. I'd suggest go ahead and push on this and you'll see what I'm talking about. You'll get a normal curve. It's called a Galton machine. I have one in my office. One of my dad's friends made me one. Or maybe you have a game we had when we were kids called Pachinko. It reminds me of that too. I think the main thing I want to get to in this is that the normal curve has two parameters. It has a mean and it has a variance. The mean is going to determine where the bell of that is. So here's mu, and variance is just the spread. Well, variance is here, but standard deviation is the spread, the square root. So here's a nice normal curve. Mu is always going to be where the bell is, and sigma is how stretchy it is or how slim it is. And let me give you the density function. That's really what you need. So imagine, again, you're doing all these problems with integration. You have a continuous curve, and there is f of x. It just looks really nasty. Make sure the sigma is outside the square root of 2 pi. This x minus mu squared, the e, the negative x minus mu squared, this is what's giving you that bell-shaped. Mu is controlling, shifting left and right where the center is, and you see the sigmas here. This is showing you the stretchiness of it. It's shrinking or stretching it. It's not easy to verify. We could do polar coordinates, and I can show you that this is always a legal density function because it's always going to be above the x-axis, and it always integrates to 1. The area under the curve is always 1. And this is not an easy proof, so I did not prove it here. I'm just saying you can go to a website, you can use polar coordinates. I show you some different graphs. Here's a normal mu 0 sigma 1, mu 0 sigma 2. Notice it gets fatter. Mu controls where the center is. Mu 0, sigma quarter, it gets skinnier. Mu 1, sigma 1, shifted 1 right. And these all follow that equation. I would just put in mu is the mean and sigma as the standard deviation. So down here I'm trying to find, I'm saying IQs for certain set of people. The mean is 100, the standard deviation is 10. What's the probability we pick a person? Their IQ is between 80 and 100. I'm assuming IQs are continuous. It may be, yeah, they're probably discrete, right? And then we're going to put a continuous curve to it. But the probability someone has an IQ between 80 and 100, I'm going to integrate over that normal curve. Notice I'm putting in 10 for the mean. Sorry, that's a lot. I'm putting 10 in for the standard deviation, 100 in for the mean. Here's the 10 squared. I integrate, I get a number. So, I mean, going back to, what we've been doing in chapter 6, 7, define area under a curve, you're just integrating. This one just happens to have a very nasty density function. So again, for a standard, or for a normal, it's 1 over square root of 2 pi times sigma. Put in your sigma there. E negative x minus mu squared divided by 2 sigma squared. Plug and chug your mu's and your sigmas, and then integrate over the area of interest. You don't always want to, maybe you don't want to integrate, or you're on an island and you don't have the ability. That's where the normal table came from. They just said, this is a very popular distribution, so what we could do is convert it to another scale and use what we call a z-table. And I have two, I have a video on integrating, I have a video on using the normal curve, the normal table to find areas. So I'll just leave that. I guess the main thing I want out of this video is to say the normal curve, this is its density function, and to find probabilities, you integrate this function over the area of interest. So I'll leave it there, and I had two other videos on the normal, how to use the table and how to integrate. So if you have any questions, let me know, and otherwise we are just keep moving along. Let me see how I shut this thing off again. Okay, until later.